Same thing, if you just turn these plates by 90 degrees, then you get the y and z, components, so the y component of y, of b, and the z component of x tangential. So do exactly the same thing, just with the plates turned by 90 degrees. What you'll see is that then b y bar will be the y plus b over c squared b z, and we'll get e z bar equals okay. Now the last thing we need to do here is to figure out what happens if we're turning the plates this way. So if we have our plates like that and move in that direction, will that change the charge density somehow? Or what will change? What changes? Will anything change at all from static to moving? Or anything in the capacitor change? If we have it like this, then obviously we have an electric field E equals x in the x direction, right? What changes about the capacitors if we move along the direction perpendicular? Closer together, right? Does that affect the electric field? It doesn't, right? Simply sigma over epsilon, the distance doesn't go in there. So that means the x component of the electric field will just stay the same. And for the magnetic field, we do one other thought experiment. So let's assume we have some curly wire where we have some charge, some current I going through. Say this is the x direction. Then, obviously, we'll have a magnetic field E going inside this curl, right? Then this magnetic field E equals, assume there's N being the number of curls, the number of windings per unit length, right? Then the magnetic field E is just, what is it, mu naught? Is mu naught N times the current going through, right? Okay, if we now see how these things transform, what happens to the density of windings? Will that change? N is a number that's not going to change, but the length over which these windings are distributed will be the less contracted. So in a moving frame, it is certainly going to be the factor gamma larger. But what happens to I? I is the charge per time, right? So in a moving frame, I bar, charge will stay the same over the T bar. And what happens to T bar? There's time dilation, right? So the frame bar will actually be essentially time dilated gamma dt, right? So we have a gamma here. So B is the x component, Bx bar is going to be mu naught n bar I bar, but so we have 1, so this is I over gamma. So the gammas will just cancel out. So that means, just like the electric field, also the magnetic field along the direction of motion will stay the same. Okay. So, final result of that long story. We know how electric and magnetic fields are turning into each other. This kind of looks like Lorentz transformations that we've seen from space vectors as well, right? T bar being gamma t minus, or x bar being gamma x minus v times t, and similar here, so t bar being gamma t plus or minus v over c squared x. So, what do you think? Can we simply make a 4-vector out of E and B and try and see if we can reproduce these Lorentz transformations? So we know the Lorentz transformation, of course, if we have some 4-vector A, then of course A bar would be our Lorentz matrix lambda times A, or A bar mu would be lambda u, or lambda u was gamma minus gamma beta 0, minus gamma beta gamma 0, 0, 1, 0, and 0, 0, 0, 1, right? So can we come up with some kind of 4-vector that combines E and B? We have these transformations for our electric and magnetic fields. How many independent components do we have in a 4-vector? That's kind of why it's called a 4-vector, right? That's 4, right? How many components do we need for electric and magnetic fields? We have 3 electric field components, right? X, Y, Z, and we have 3 magnetic field components. So that's a little too much for simply a 4-vector, right? So we can take this Lorentz transformation concept one step further and say, well, we need something bigger, something with more entries than just a 4-vector. So the next step we can do is have not a vector, but have a tensor. So something like not 4 times 1, we have 4 by 4 entries. That would be the next bigger thing that we can do. So let's see if we can cook up something that we will call a tensor. Let's call that some t mu. So something 4 by 4. So that has t0, 0, t0, 1, t0, 2, 3, t1, 0, t1, 3, 0, t3, 0, 2, 3, right? And just like transforming a 4-vector like there, we can simply postulates that if this is something that makes sense in relativity, we can transform that into some moving frame as transforming, so starting out with the old tensor, and instead of just now multiplying with one column there for a 4 vector, we do this for all columns here. So we go through indices in one column, and we go through indices in the other column. Effectively, for both indices, we have these Lorentz transformations to the Lorentz matrix. So that is simply the two-dimensional generalization of Lorentz transforms of 4 vectors. All right. So with a 4 vector, we had too few entries to have 3 magnetic and 3 electric field components, right? How many entries do we have in a thing like this, in a tensor? 4 times 4, right? But 16, that's obviously way more than we need. Can we put some constraints maybe, that we say we don't actually leave all of them free here? For example, we can say is that thing may be symmetric. So that means if we change the indices, u, from this side to this side, we get the same, tu, u. In that case, so this equals that equals that. Independent entries are essentially just in, say, the upper half. The lower left is then just a mirror. So then we have 4 plus 3 plus 2 plus 1, 3 entries. That gives us 4 plus 3 plus 2 plus 1 is 10, right? It's still too many. What if we say this is anti-symmetric? That means T u would actually be minus T u. So that means the tensor is actually just so some T 0, 0, T 0, 1, 0, 2, T 0, 3. But then whatever is here, T 1, 0 must be minus T 0, 1. This is T 1, 1. 2, 3, and now this mirror here must be negative, must be minus T02, this must be minus T12, T22, T23, and here minus T03, minus T13, minus T23, and T23. Do we still have 10 free entries here, or can we say more? What if mu equals u? So if mu equals u, then we have T u. U must be minus T u, right? So the diagonal elements must be equal to the negative. There's only one number that can do that. What does that mean? If the number is equal to its negative, the number must be 0. Only 0. So if we have the symmetric tensor, then everything on the diagonal actually must be 0. 0, 0, 0. And then suddenly we have 1, 2, 3, 4, 5, 6. We suddenly have only 6 free entries. So now the only trick is try to figure out how does it make sense if we have, so if we now somehow stray our E, X, Y, Z, and E, X, Y, Z into these entries, do these Lorentz transforms, can we end up with these transformations? We figure out how to do that. We know how we can produce an anti-symmetric tensor that gives us the fields, and this tensor transforms with the Lorentz transformation standard. So let's see what this actually means for these transformations. So let's maybe start out with, so we know T00 is 0, antisymmetric. Let's do T01 bar. That must be lambda 0, mu, lambda 1, mu, T, mu, mu. Right? That is simply this written out for mu equals 0 and 1. Maybe to make it consistent, mu was 0 and 1, so make that sigma, so let's set sigma lambda, right? Doesn't matter what I call them, but this way it looks exactly the same. We set mu and mu to 0 and 1. Okay, what's the, now I have erased the lambda here, so lambda is again gamma minus gamma beta, 0, 0, minus gamma beta, gamma 0, 1, right? Okay, so lambda 0, top row has entries only in 0 and 1, right? So this would be, so lambda 0, we can put 0, and we have, again here, lambda 1 has only 0 and 1, so we can start with lambda 1, 0, for example, as T0, 0, plus 0, 1, that is one that has an entry, lambda 1, 0, T1, 0. Then plus lambda 0, 0, lambda 1, 1, T 0, 1, plus, I've forgotten 1, here this lambda 0, 1, lambda 1, 1, T 1, 1. That's everything where the lambdas are not 0, right? The lambda 0, 2 and 3, or lambda 1, 2, 3 are all 0. So that's all combinations that go in. Now, first thing, the diagonal elements were 0, right? That is 0, so that comes off. 1, 0, 9, 0, 1, okay, 1, 1 is 0, right? Diagonal element. That's that. And what we can do, since lambda 1, 0, this is anti-symmetric, this is lambda 1, 0, is the negative of this one. So this actually gives us minus lambda 0, 1, right? Alright, so what we have is T0, 1. We have this one here, lambda 0, lambda 1, 1, and then with the negative, lambda 0, 1, lambda 1, 0, equals T0, 1. What is that? 0, 0 and 1, 1, that's 0, 0, that's 1, 1, times squared, minus 0, 1 is here, 1, 0 is there. So both is minus, minus is plus, but there's a minus here. Gives us gamma squared, beta squared, right? So that is T0, 1, gamma squared, 1 minus beta squared, and that is 1 minus beta squared is 1 over gamma squared. This is 1 over gamma squared. So this is just T01. So, first thing we found is that T01 bar is the same as T01. So, that means immediately that our T01 must be either the electric field X component or it can be Vx, right? So that would work both ways. We do that exercise one more time with, say, T02 bar. That is, okay, always fun. So this is lambda 0, sigma, lambda 2, lambda T sigma lambda equals. So for the zeros, again, we have lambda 0, 0. Say lambda 2. The nice thing with lambda 2 is that it only has an entrance into 2, right? Everything else is 0. So here we go already only lambda equals 2 is non-zero. So this will be lambda 2, 2, that's 1. T 0, 2 then. And then there is lambda 0, 1. Lambda 2, 2, T 1, 2. And everything else is 0. Plus lambda 0 is only 0 and 1, 2, 3 and 0. So this is lambda 0, 0 is gamma, lambda 2, 2 is 1, so this is gamma T1, 2. Lambda 0, 1 is minus gamma beta, lambda 2, 2 is 1, so minus gamma beta T1, T0, 2. Okay, so this is gamma T0, 2 minus beta T1, 2. Alright, see, when we have something like that, it could be something like this, right? Or could be that. So two solutions here. We can have sort of T02, T02 could be, well, what we have here, that could be Ey. That means that T12 must be Bz modulo some C, right? T12 would be actually C times Bz. Or we can identify this here, right? Or we can have T02 equals Bz. And then T12 must be E y over C. And so if you figure all the other transformations out as well, and leave that for you as exercise. It's essentially the same thing, just do these summations. If we do that, then we find the form of the field tensor. And as we've seen here, there will always be two different ways that you can associate this so that the Lorentz transformations still work out. So there's one that we call F mu nu. F. That has the form for 0 here. And we have x e y over c e z over c. Then of course this has to be the negative of that. Y over c z over c. 0. And the magnetic fields are these remaining components of z minus x z minus and see that I don't even remember all this, so I won't expect you to remember the exact form of the exam either. If you need it, I will give it. So this is one way to do that. So now with our Lorentz transformations, we get the field transformations as we've derived them. There's another tensor that's called G mu nu, for which it works in exactly the same way. So in that case, we have, so remember we said, for example, for the 0, 1, we could choose either EX or BX. So this was the choice of EX. If we start here with EX, we get BY and BZ here. And of course, the negative here minus Y minus Z, 0, 0, 0. And then the electric fields are minus minus E Z over C, E Y over C, X over C, and here the derivative term, so plus C minus over C, E X over C. So those are our electromagnetic field tensors. And you'll see that we can do essentially all of electrodynamics just in terms of these tensors. Right? Everything nice, compact, just in terms of these tensors. Say, before we move on, we should probably get some coffee. And we'll probably continue that a little bit next week as well. But so for now, any questions? Does this make sense so far? Let's say let's grab the coffee and keep back it.